Welcome everybody. This is our series of video solutions to Superquiz 3 from my Math 250A class. That's multivariable calculus here in spring 2021 at Cal State Fullerton. So this is the video solution for problem 1 on the exam, which is a very straightforward procedural problem. We're given two vectors and we're asked to find the cross product. So everybody has their own favorite way of doing it. So I'm not going to probably tell you anything new, or maybe even do it the way you like to do it, but I'll show you the way I like to do it, and maybe even another way, and that's basically, like, you can do it any way you want. I don't really worry about what method. You just need to be able to compute a cross product, because in multivariable calculus, particularly when we get to the vector calculus stuff, we are just using cross products all the time. So my approach is to treat it like a elementary multiplication problem. I've just lined it up exactly in this way. And what I do is I'm going to cover up the first column when I'm trying to get the first component. So I have to multiply diagonally in both directions and subtract one of those directions. So I'm going to go left to right first. Negative 3 times negative 4, which is 12, minus... You go the other way, do 2 times 1, which is 2. Okay, 12 minus 2 is going to be 10. Okay, then we go to the second column. And when I do the second column, I do the same trick where I'm going to multiply diagonally, except I do it in reverse. So I'm first going to do 2 times 0, which is 0. And I'm going to subtract, and I'll go the other way, 5 times negative 4. So that's negative 20. So 0 minus negative 20, which is 20. All right, now I go to the third column, and I cross out that third column, and I'm going to go left to right and right to left. So I, again, start from left to right, and I do 5 times 1, which is 5, minus, okay, negative 3 times 0 is 0. 5 minus 0 is 5. And so the cross product of u and v is going to be 10, 20, 5. Okay, let's see another way somebody could do it. So some people like to use determinants. So the determinant of the 3 by 3 matrix, where you put I, j, and k. Remember, I represents the unit vector in the x direction, so 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. I put those in the top row. Then I'll put u into the middle row. So that'll be 5, negative 3, 2, and I'll put v into the bottom row. So 0, 1, negative 4. And I'll compute the determinant. So when I compute the determinant, we'll say I want to get the I component. That's going to be everything multiplied by I. So there's sort of two ways when you take the determinant to get something multiplied by I. One of them is when you multiply this diagonal together. So you choose I, and then you can either do negative 3 times negative 4, or the other way, once you've chosen I, is to do 2 times 1. However, when you do the 2 times 1, that version, you're going backward, so it picks up a minus sign when computing the determinant. So negative 3 times negative 4 is 12, minus 2 is 10i. Okay, then we do the j. And when you do the j, there's two ways. You could either pick the 5 and the negative 4, or the 0 and the 2. Now, if you take the 5 and the negative 4, then again, this is sort of doing it backward, or if you like, we're taking the second position, the first position, and the third position. And if you write that out second position, first position, and then third position in the 3 spot. This corresponds to basically one transposition, one swapping of the numbers 1 and 2. And because that's one swap, that's why you get a negative. So if we do the 5 and the negative 4, you get one swap. Now, if we do the this position, the 3 and the 1, so this would correspond to 1, 2, 3. Okay, so let's see. 1 still goes to 2, but now the second row in this way would go to 3, and then the third row would go to 1. So here it actually would require 2 swaps to get back to 1, 2, 3. Right? You could swap the 1 and the 2, and then you'd have to swap the 2 and the 3 to get up. So 2 swaps gives you a positive. So that's why it's positive that way. If you haven't seen this before, that's fine. It's a way of thinking about the determinant in a less formulaic way. It's actually defined in terms of these. When to get the sign, it's defined in terms of how many different transpositions it would take you to get back to this original list 1, 2, 3. Don't worry about it so much. The important thing to know from a formulaic point of view is if you choose this j, when you choose the ones going from left to right, that gets a negative sign. From right to left, that gets a positive sign. So in this case, you'd have a positive 2 times 0 and then negative 5 times negative 4, which will give you 20. And then to get the k, do the same thing. You can go 5, 1 here, and that would give you the positive version, or you can go backward, and that'll give you a negative version. So we have 5 minus 0 is 5. So 5k. Alternatively, if you're doing these determinants, you might write it out in a slightly different way, where you say, okay, let's do I times negative 3 times negative 4, which would be 12i. And then you keep going along these diagonals, overlapping if you have to. So then you go j times 2 times 0. Okay, that's nothing. Then you go k times 5 times 1. That'd be 5k. And then, once you got to the end, you turn around and go backward. You say, okay, now I have negative 3 times k times 0. That's nothing. Then I have negative 5j times negative 4. That's going to be 20j. And then the I and a 2 times 1 with a negative, so negative 2i. And again, if you put these back together, you'll have 10i, and then, well, these are already 20j and 5k. So that's another way to do it. Let me show you one more way, and this is maybe not the best way for a problem this complicated, but it's good to know that such a way exists. So I'm going to write the original vector u. Oops, not a unit vector. I'm going to write the original vector u as 5i minus 3j plus 2k. And my original vector v, that just becomes j minus 4k. Oops. Now, if I want to find the cross product of u and v, I can instead write this as the cross product of these expanded versions of the vectors. So cross, here we go, j minus 4k. Now, because of the distributive laws that hold for the cross product, I can break this up as 5i cross j minus, this minus is coming from there. So let's see, we have 5 and negative 4, so that's going to be minus 20. Oops, 20i cross k's. So we'll move on to this j. So we have minus 3 times 1, so minus 3 j cross j's. Let's see, minus 3 and minus 4 is 12 j cross k's. Then we'll move on. We have 2 times 1 is plus 2 k cross j's. And then 2 times negative 4 will be minus 8 k cross k's. Okay, now first observation is whenever you take the cross product of a vector with itself, you get 0. Right? If you like, it's because they generate a parallelogram of, it's a degenerate parallelogram, so its area is 0. So the cross product, we know the magnitude of the cross product will give you the area of that parallelogram. So this j cross j here has to be 0, and this k cross k has to be 0. All right, what about the ij, ik, etc.? Well, we can use this nice picture. So we can draw the 3, and we put some little arrows here. This tells us I cross j is k, j cross k is I, and k cross I is j. This is all part of it being a left-handed, excuse me, a right-handed coordinate system. And if you go backward, of course, then you get negatives, because when you reverse the order of a cross product, you get a negative sign. Okay, so I cross j from here is equal to k. And I cross k, well, that's going backward, so it'll be negative j. And j cross k, that's going forwards, you get I. K cross j, well, you're going backwards, you'll get a negative I. All right, so we've got everything. We can put it all together. How many i's do we have? Let's see, 12 and 2 times negative 1, so 12 minus 2 is 10 i's. And J's, let's see. Negative 20, oh, there's a positive, so that's 20J. And, oh, that's the only J, so plus 20Js. And K's, there's only one of them, 5K. Okay. So we have a third way of computing the cross product. There's more. I'm not going to lie to you. Again, everybody has their favorite. Here are 3 of mine. You pick your favorite approach.